Hello, welcome back. We are discussing the last section in Chapter 3, Section 3.5, Additional Applied Optimization. So the learning objectives for this section were all sort of wrapped up together, and basically the videos for this section are mostly going to be about this middle learning objective, model and analyze a variety of optimization problems. So our task is basically going to be take a bunch of examples and try to extract some sort of information out of them. So there's no new definitions, no new theorems, no new formulas from this section. Basically what we're doing is taking word problems for which the function that we'd like to maximize is not handed to us right away. They may give us information that helps us build this function, and then we're in charge of finding maximum value, minimum value, etc., much like we did in the previous section. So we're just going to do some examples. This first video will do one classic sort of geometry example. So we're going to presume that we have a rancher. We want rectangular enclosures for the animals. So the animals are going to get divided into two spaces. So we'll have two enclosures. We'll just, for the sake of picture drawing, have this divided in half vertically. So I have a vertical line separating these two enclosures. And then we've got fencing that's got to go around and then in between the enclosures. We know that she's got 864 yards of fencing altogether, and the goal is to, given those constraints, figure out what dimensions give the maximum area. And then what is that area? Okay, so the first thing to figure out is the thing that we'd like to maximize. So maybe I'll go back just to review this. What is the area? So here's the piece that we should really be focusing on, maximum area. So that's the goal. So all of my targets from this point forward are on figuring out area and what its maximum might be. So given what we've got, it's just a bunch of words so far. Nobody gave us a formula, but we know that the shape of the region is rectangular. So we ought to be able to figure out a formula for area. We know in general area of a rectangle is length times width. So we've got that to go off of. And just a picture to help establish this. Here's our rectangular enclosure, so maybe this is the horse side and this is the cow side, for instance. At any rate, the problem is that we've got two variables in our area formula. That's generally challenging to optimize that way. Now, in the future, in Math 242, we will figure out how to optimize things with more than one variable, but for the time being, it would really be great if we just got down to only lengths or only widths. And this is where we have to make use of more information given to us in the question. In the setup of this problem. So remember that we were told the total amount of fencing that was available. So fencing required is this whole perimeter, so the distance around the outer edge of the rectangle, plus this fencing that separates the two enclosures. So it's not quite just 2L plus 2W. The rectangle itself would be distance all the way around. That's our typical 2L plus 2W. But we've got this other piece here, and we have to account for that in our surface area, well, our perimeter. So this vertical segment is what gives us one additional W in our equation. So then altogether, the total perimeter is 2L plus 3W. However, we know what this total ought to be. It should be 864 yards. That was given to us in the setup of this problem. So here's the deal. We're going to use this equation down here as a helper to get rid of one of the variables in our area equation. Okay, so just reiterating, the thing has two unknowns in it. We're going to get rid of one of them using this helper equation. 2L plus 3W equals 864. So we're going to use this to solve for one of the variables. It really doesn't matter which, but I'm going to pick length to go after. So we do our usual solving strategies. We've got 3W getting subtracted over to the other side, and then divide both sides by 2. Okay, so we have L now in terms of width. So we'll take our area equation and replace L with this big expression. So here's where L used to be, and now we're going to use that solved equation from the previous slide and replace L with this thing. And just a little tidying, so distributing the W to each of these terms, we get 864 over 2 is 432, and then that's times W. And then we have 3/2, which I've written as a decimal just because, I don't know, it felt like no fractions, I don't know. And then that's W times W, so we're actually at W squared. This is a much more comfortable place to be, and it's kind of the place that we were at most frequently in 3.4, where we were handed a formula to begin with, and it's our job to find max min. Okay, so we're in charge of finding a maximum value for this, and as usual, this is where we go after critical points. Critical points most typically are found by setting the derivative. So if we do some power rule with that, 432 minus, I guess, down to 3w, taking this derivative and setting it equal to 0. So we want 0 equals 432 minus 3w, which is pretty straightforward to solve and actually gives us a whole number, which is convenient. So 432 divided by 3, solving for w, gives us 144. Okay, there's only one critical point, and oftentimes we can get away with saying, look, if they told us to maximize area, and we found one critical point, then let's make sure that or let's just say, well, fine, it must be the maximum. That's not totally safe if we're looking for absolute max or absolute min, because we also have to worry about the endpoints. But a way to get around this is that if we do the second derivative test for absolute extrema, then we're testing the second derivative of this function, which is actually a pretty easy thing to compute. Second derivative is not going to be hard to find because there's our first derivative. As long as what we come up with is a negative number at this critical value, then we should be guaranteed that this function has an absolute maximum. And that's the case. If we take the derivative of our a prime, so we get a second derivative, we just get a constant, -3. So it doesn't even matter if we plugged in 144 for w, we're going to get -3 no matter what input. No matter what input we dump in there. So in particular, since the critical point at 144 would give us an output of -3 for the second derivative, then we know that this must be a maximum. And then we're going to go back, now that we know the width, we're going to go back and get the length value. And for this, we could go all the way back to the 2L plus 3W equals 864, but we might as well go to the form of that equation where L is already solved for. So if we're going to do the hard work of moving things around and getting L by itself, we might as well make use of it later on and save ourselves some effort. So if the goal is to find length, then we can go back to this form. Dump in 144 for W, and get something maybe not that surprising, but that the length is equal to the width. So now we have that the total space should be a square. Then the enclosures are each 144 yards wide and then 72 yards long because we're cutting that 144 in half. And so the total area in each of those enclosures is 72 times 144, which ought to be 10,368 square yards. So there's the example for this video. Again, I just want to reiterate what this section is about. What we had to do for this problem was to find the function that we wanted to maximize to begin with. Nobody handed us an area equation. So I had to read very carefully, figure out that I wanted to maximize area, write an area equation, and then use some of the other information in the question to get rid of those variables. So we got down to just area as a function of width, and then we did our typical critical point solving strategy. We'll be back in another video with another example.